Today we will discuss about chapter number 3, Mechanism of Organic Reaction. Introduction. During the study of organic chemistry, we come across numerous reactions with the organic compound undergoes. As we study these reactions, we not only want to know which reactant give rise to which product, but we also interested in knowing how it happened. Do the reactant change directly into product in a single step, or does the reaction take place by several steps through the formation of a reactive intermediate? The complete description of how a particular reaction takes place is called mechanism of a reaction. It tells us about bond or a broken and in what order, and which bond are formed and in what order. It also tells us what kind of intermediate are involved and what are relative rate of different steps. We shall now discuss some important notation and basic concept involving the study of organic reaction and their mechanism. Important notation. Reaction of organic compound involving the breaking and making of a covalent bond and the movement of electron from one side to another. To indicate this change, certain notation involved the use of a different kind of arrows having different adoption as described below. Curved arrow notation. It is a very useful notation in which a curved arrow indicates the movement of electron as bond in a reactant are broken and new bond in product are formed. It means that an electron pair moves from the atom at the tail of an arrow to the atom at the head of an arrow. This is illustrated below with the help of a reaction between water and a halogen chloride. The electron pair moves from of H2O to H of HCl. The bond between H and Cl break and the electron pair move to Cl. The electron pair that moved from O from a new bond with H to give H3 opposite hydronium ion. The electron pair of HCl bond goes to Cl to form Cl negative ion. Similarly, reaction between acetylene and amide ion to form acetylide ion and ammonia may be shown as follows. Half-headed arrow. As we will discuss in session 2.3, sometime a bond between two atoms break in such a manner that each atom get one electron as shared pair. To represent this type of a symmetrical bond breaking and bond making, half-headed arrow are used as shown. It may be noted that half-headed arrow is used for showing movement of a single electron while a full-headed arrow is used for a pair of electrons. Double-headed arrow. This type of arrow are placed in between the various conical structure of a substance which exhibits resonance. This is indicate that the actual structure of a hybrid of this structure which are hypothetical and not real. For example, double-headed arrow are placed between the two major conical structure to benzene to indicate that the actual structure of a benzene lie in between these two structures which does not have any real existence. Type of bond cleavage. Reaction for organic compound always invertibles take place through the breaking and the formation of a covalent bond. Depending upon the nature of a given organic compound, the nature of attacking reagent and the reacting condition, a bond between two atoms of a molecule may be cleaved or broken in a different way, producing different type of reactions. The different possibilities are isolated between the considering a covalent bond between two atoms A and B. Homolytic cleavage or homolytic fission or homolysis. This involves the breaking of a covalent bond in such a manner that each atom separates with one electron of a share pair. This leads to the formation of high reactive neutral particle containing odd or unpaired electron and known as a free radical. It may be seen that the homolytic cleavage of bond is shown by using half-headed arrow in a pair. Heterolytic cleavage or heterolytic fission or heterolysis. This involves the breaking of a bond in such a way that both the electrons of a shared pair are carried away by one of an atom. If A is more electric than B, then negative charge on A appears and B appears positive charge. If B is more negative than A, then B appears negative charge and A appears positive charge. Heterolytic fission lead to the formation of a charge or ionic species. On one have a positive charge or another have a negative charge. If both the charged electrons are taken away by A, it would be converted into anion and B into cation. On the other hand, if both the shared electrons are retained by B, it would be changed into anion while A would be formed cation. As above. Quite often the ionic species formed by heterolytic fission bear the positive and negative charge on a carbon. Such ionic species are known as carbocation, early called carbonium ion or carboanion. According to carbon carries positive or a negative charge. It may be mentioned that if a particular covalent bond can undergo either homolytic cleavage or heterolytic cleavage under different conditions, the bond dissociation energy for homolytic cleavage is considerably different from the heterolytic cleavage. In general, the value of homolysis are low while they are quite higher for heterolysis. For example, the bond dissociation energy of carbon and chlorine bond in chloromethane for homolytic and heterolytic cleavage are 351 and 449 kilojoule per mole respectively. Homolytic fission. Free radical methane plus free radical chlorine. Heterolytic. There is positive charge on methane and negative charge on chlorine. Reaction intermediate. The student is already familiar with the fact that in organic reaction the starting substance seldom change into the product directly in one step. On the other hand, reaction first change into intermediate substance. For example, called reaction intermediate, which ultimately yield the product. The reaction intermediate are generally very unstable and reactive substance which cannot be even isolated. We will now brief details with the main reaction intermediate which we often come across in organic chemistry. Carbocation, earlier called carbonium ion. What are carbocation? A carbocation is a cation in which positive charge is carried by a carbon which has only 6 electrons in its valence shell. For example, CH3 positive and CH3CH2 positive are a simple carbocation known as methyl cation or ethyl cation respectively. A carbocation may be assumed to be a fragment of a molecule from which an atom or a group single bonded to a carbon get removed along with the pair of a bonded electron. For example, if a bromine ion is removed from a molecule of a tetrabutyl bromide, tetrabutyl cation while would be formed as shown. Tetrabutyl bromide, tetrabutyl carbocation. Carbocation are very short-lived and highly reactive species. The reactivity of a carbocation is due to their tendency to complete the octet of electron-deficient carbon. As a result, carbocation undergoes a variety of reaction. Formation of a carbocation. Carbocation can be generated in many different ways. Some of the reactions in which they are formed are given below. First, direct ionization. The carbon-halogen bond CX in many organic halides generate carbocation in the presence of highly polar medium. For example, tetrabutyl chloride converted into tetrabutyl cation and chlorine anion. This method is of particular importance in the formation of relative more stable carbocation. Second, by the protonation of unsaturated carbon. Unsaturated compound as alkenes, carbyl compound and nitrile furnishes carbocation are treated with protonated donation solvent. For example, if we add carbonyl group with the hydronium ion give alcohol compound. For compounds containing an atom with lone pair of electron, when an organic compound having lone pair of electron on an atom is treated with acid protonation of this atom take place. This is followed by the elimination of a simple molecule containing this atom to furnish a carbocation. For example, alcohol plus protonated hydrogen ion give protonated alcohol converted into carbonation plus water. Ether plus hydronium ion give protonated ether and converted into carbocation plus alcohol. By the decomposition of a diazonium salt, for example, primary amine in the presence of HNO2 give diazonium cation and change into carbocation. by the action of a superacid or alkyl fluoride. For example, fluorine in alkane plus superacidic SbF5 in the presence of FSO3H give carbocation plus SbF6 negative. Note, the term superacid is used for some exceptional strong acid solution such as SbF5 plus HF or SbH5 plus FSO3H dissolved in SO2 or SO2CIF. Structure of a carbocation. The positively charged carbon of a carbonation is in sp2 state of hybridization. The 3sp2 hybridization orbital which lie in a same plane are involved in the formation of 3 bonds with other atom. Unhybridized p orbital remain vacant. Thus the carbocation has a flat structure as represented on the right hand side. The bond angle around the positive charged carbon is nearly 120 degree each. Classification of a carbocation and the order of stability. Carbocation are classified as primary, secondary and tertiary according to the carbon bearing the positive charge as primary, secondary, tertiary in nature. In addition, the methyl ion having only one carbon is treated as a special case. Methyl cation, ethyl cation, primary. Isopropyl cation, secondary. Tertiary butyl cation, tertiary. It has been established that the order of stability of a carbocation is decreasing in order: tertiary, secondary, primary, methyl. Explanation of relative stability of alkyl carbocation. A basic principle involving in discussion the relative stability of a carbocation is that how does a given factor influence the magnitude of a positive charge carried by electron deficient carbon of a carbocation. It is apparent that any factor which tends to disappear the positive charge by discussing it over the rest of a molecule stabilizes the carbocation. In contrast, any factor which tends to intensify the positive charge destabilizes the carbocation. The relative stability of alkyl carbocation are given above can be explained in terms of including effect and hyperconjugation in terms of above principle. First, inductive effect. This is the main factor operating in determining the relative stability of the carbocation as well. Well known, the alkyl group are more electron releasing than hydrogen. As such, as alkyl group attached to positive charged carbon of a carbocation tends to release electron toward the carbon due to its plus I effect. In this way, the positive charge on a carbon get disappear. This dispersal of a charge stabilizes the carbocation. Now, the more number of alkyl group, the greater the dispersal of a positive charge, and therefore more the stability of a carbocation. That is why a tertiary carbocation having 3 alkyl groups attached to the positive charge is more stable than a secondary carbocation with 2 alkyl group. The secondary ion in turn is more stable than a primary carbocation having only 1 alkyl group. The methyl carbocation does not have any alkyl group and is therefore the least stable. Tertiary carbocation, maximum dispersal of positive charge, maximum stability. Secondary carbocation. Primary carbocation, methyl carbocation, least dispersal of positive charge, least stability. It is quite evident that presence of electron withdrawing substituent minus I effect will destabilize the carbocation by and intensify the positive charge on carbon. Second, hyperconjugation. The concept of hyperconjugation is also to some extent responsible for the observing order of a relative stability of a carbocation. Hyperconjugation can take place here through the overlapping of sigma orbital of alpha carbon hydrogen bond of alkyl group and the empty p orbital of a carbocation. Taking ethane cation to represent a carbocation in general, delocalization of electron through sigma and pi orbital having may be shown as due to overlapping the delocalization electron bind together 3 atoms, 2 carbon or 1 hydrogen to some extent. In terms of resonance, the above situation may be depicted as the net result is that in actual structure, carbon-hydrogen bond is slightly lesser than a single bond. The carbon-carbon bond have some double bond character while the positive charge is partially accompanied by hydrogen atom. This partially accommodation of a positive charge over hydrogen lead to dispersal of a charge and consequently stable the ion. In methyl carbocation, no such dispersal of a charge is possible but hyperconjugation does not take place. In ethyl carbocation, which can which contain 3 alpha hydrogen. The positive charge can be disappear over 3 hyperconjugation structure possible in addition to a normal structure as below. In isopropyl carbocation, which contains 6 alpha hydrogen, there will be 6 hyperconjugation structure possible. In tertiary butyl carbocation, which contain 9 alpha hydrogen, there will be a 9 hyperconjugation structure possible. As the number of a contributing structure and with that dispersal of a carbon become more, the stability of a carbocation goes on increasing. Thus, the relative stability of alkyl cation may be due to combining the inductive effect and hyperconjugation, although it is usually explained in terms of inductive effect alone. Third, conjugation of a positive charge with a double bond or a benzene ring resonance stabilization. The carbocation in which the positive charge carbon is conjugated with a double bond or a benzene ring have been found to have extra stability. This has been attributed to resonance effect involving the electron of a double bond. For enhanced, allyl cation is a resonance hybrid of a two equivalent structure as shown below. It is apparent that positive charge of a carbon of a carbocation get dispersed over two carbon atom. Hence, the allyl cation acquire greater stability and is found to be more stable than a simple alkyl cation. Similarly, benzyl carbocation is greatly stabilized by the resonance as shown below. It is the evidence that carbocation having more than one phenyl group attached to a positively charged carbon would be still more stable. This is because there will be a greater dispersal of a positive charge due to large number of contributing structure. According to diphenyl methyl carbocation would be more stable than a benzyl carbocation. 3 more contributing structures. Similarly, triphenyl carbocation would be still more stable. 6 more contributing structure. In fact, triphenyl methyl carbocation is so stable that some of its salts such as a prochlorate can be isolated and stored for months. Effect of substituent on the stability of a benzene carbocation. In it can be readily understood that the presence of a electron releasing group of ortho and para position of a phenyl group with respect to positive where a CH3 positive group is attached will tend to further stabilize the benzyl carbocation. On the other hand, the presence of electron withdrawing group at these positions would have the positive effect. For example, the order of stability of following substituent benzyl ion is. Fourth, instability of phenyl and phenyl carbocation. The carbocation in which positive charge is carried by a double bond carbon atom such as vinyl and phenyl cation are found to be highly unstable. This is because these ions do not undergo the resonance stabilization at all. The reason for lacking of resonance is that the vacant orbital of a carbon carrying the positive charge is perpendicular to the double bond and therefore it cannot participate in a resonance. Determination of relative stability of a different kind of a carbocation. It is evidence for the above discussion that the stability of carbocation is primarily related to the dispersal of a charge carried by a positive charged carbon. The dispersal of a charge may be due to inductive effect, hyperconjugation effect, or resonance effect as explained above. The relative stability of a different kind of carbocation can be measured in terms of a heterolytic bond dissociation energy leading to the formation of a carbocation. On the basis of this value of decreasing order of stability of some of a common carbocation are given ahead. Tertiary decreasing in order: tertiary benzyl, isopropyl, allyl, N-propyl, ethyl, vinyl, phenyl, methyl. It may be pointed out, however, that benzyl, isopropyl, and allyl carbocation are almost equally stable. Similarly, vinyl, phenyl, and methyl carbocation has nearly the same stability. Problem 3.1. Arrange the following carbocation in order of decreasing stability. We can see this is the tertiary. We can see at which is primary, secondary, and tertiary. According to this, we arrange this. Problem 3.2. Which of the following carbocation is most stable and which is the least stable? The most stable compound have resonance. For example, there is allylic compound, and least there is no resonance, no hyperconjugation, or somewhere least amount of inductive effect. Problem 3. Arrangement of the following carbocation in order of distability. Justify your answer. According to we see there is a inductive effect, resonance effect, which have more. In the cyclic compound, we saw which group is attached, withdrawing or releasing group. Rearrangement of a carbocation, one or two shift. An important feature of a carbocation is that they can undergo rearrangement reaction to form more stable carbocation. These rearrangement involve the shift of either hydrogen or allylic or aryl group along with its electron pair from an adjacent carbon to positive charged carbon. Such shifts are known as one-to shift. The shift of hydrogen is known as one-to shift hydride shift, while that of alkyl group is known as one-to alkyl shift. The cation thus formed contain a new charge center and a more stable than the original carbocation. For example, 1,2 hydride shift. N-propyl cation 1 degree shifted into 1,2 hydride shift. Isopropyl cation 2 degree more stable. 1,2 methyl shift. Nanopentyl cation converted into 2-methyl 2-butyl carbocation more stable. The rearrangement reaction of a carbocation are discussed in detail at later stage in a book. What carboanion? What are carboanion? A carboanion is an anion in which a negative charge is carried by a carbon. The carbon has a 3 bonds with one or more other atom and possesses a lone pair of electrons. For example, C triple bond CH with negative charge is a simple carbon anion known as acetylide ion. A carboanion may be assumed to be a fragment of a molecule when one of an atom or a group single bonded to a carbon is removed without the bonding pair of electrons. For instance, removing of a hydrogen of a methyl part of acetaldehyde molecule of hydrogen ion result in the formation of a carboanion as shown below. Carbanion constitute highly unstability and one of the most reactive reaction intermediate of organic chemistry. They are very frequently involving in the reaction of aldehyde, ketone, ester, etc. Their reactivity is due to the fact that the negative charge carbon in them has got a lone pair of electron. It has a strong tendency to donate their pair to some electron deficient species. Therefore, carbanion easily participate in many reactions. Formation of a carbene. There are two main methods by which carbanions are generated as given below. First, by the dissociation of a molecule in which an atom or a group single attached to a carbon leave it without the lone electron pair. That is, in most of the cases, the leaving group is a proton and hence a base is requested to facilitate the process. Thus, the formation of a carbanion is an acid-base reaction. Since the presence of electron attacking substituent such as carbonyl, cyano or a nitro group on the carbon carrying the hydrogen make the hydrogen relative more acidic and therefore more easily removable as a proton. The generation of a carbanion from such compound play a very important role in organic reaction. For examples, to remove a proton from a hydrocarbon, very weak acid, very strong base such as sodium amide in a liquid ammonia has to be used. For example, ethine in the presence of a liquid ammonia give ethine ion plus ammonia. But aromatic compound of a type trypene methane generate carbanion very easily in presence of a base. It may be noted out that apart from a proton's other leaving group are known as to lead the formation of a carbanion. For example, by the addition of a nucleophilic to the carbon-carbon multibond. But this type of addition occurs only when the double bond is activated to a nucleophilic attraction by electron withdrawing groups such as carbonyl, cyano and nitro group. Structure of a carbanion. The negative charged carbon of a carbanion is in a state of sp3 hybridized so that the hybridized orbital are directed toward the corner of a tetrahedron. 3 of the hybrid orbital are involving in the formation of single bond with other atom while the 4th orbital containing a lone pair. The carbanion has disordered tetrahedral or pyramidal structure as shown in the right hand side, but the bond angle around negative charge carbon are less than 109 degree 28 minutes. This is because lone pair repulsion is greater than bond pair repulsion. It must be pointed, however, that in case of a carboanion in which negative charge carbon having the lone pair of electron is in conjugate with the multi-bond, the carbon anion has planar structures. Some common example of carbon anion having planar structure are given below: allylic carbon anion, benzyl carbon anion, acetaldehyde carbon anion. Classification of carbon anion and their order of stability. Like carbocation, carbon anion are also classified as primary, secondary, and tertiary carbocation, according as negative charge is carried by a primary, secondary, and tertiary carbon. In addition, methyl carbon anion is considered to be a special case. Thus, we have methyl carbanion, ethyl carbanion primary, isopropyl carbocation secondary, tertiary butyl carbocation tertiary. The order of stability of different classes of carbanion have been found to be decreasing in order: methyl, primary, secondary, tertiary. Explanation of relative stability of a carbon anion. Inductive effect. The above order of stability of primary, secondary, tertiary carbanion can be justified on the basis of electron releasing plus I inductive effect of alkyl group. Due to this effect, the alkyl group tends to increase the electron density on a negative charged carbon. As a result, the carbon anion become less stable and more reactive toward electron deficient species. Now, the greater the number of alkyl group in the carbon anion, the more would be it reactive and less it stabilized. This is in keeping with the order of stability given above. It is the evidence that the presence of electron withdrawing substituent minus I effect such as NO2, carbene, such etc. will be stabilize the carbon anion by dispersing the negative charge on carbon. For example, para-nitrobenzene carbanion is more stable than this due to presence of electron withdrawing group NO2 group. On the other hand, presence of group having plus I effect such as R, RO, OH, etc. will destabilize the carbanion by intensify the negative charge. Second, hybridization. The relative stability of some carbon anion can be also be compared in terms of hybridization. For example, let us consider the following carbanion: alkyline carbanion Sp 50% S character, alkyne carbanion Sp2 33% S character, alkyl carbanion Sp3 25% character. State of hybridization of a negative charge carbon and percentage of S character. It may be noted that hybridized orbital has greater S character, has relative more electron attaching tendency or electronegativity than orbital having less S character. At the same time, the greater the electronegativity of an atom, it can accommodate negative charge more easily. Therefore, the negative charge carbon of alkyl ion can accommodate negative charge more easily, and therefore the alkyl ion is more stable than alkyl ion, which is turned in more stable than alkyl ion. Third, resonance or conjugation. As in a case of a carbocation, even the carbanion which exhibits resonance or conjugation having extra stability due to the dispersal of a negative charge as shown below for alkyl carbon anion. Similarly, benzyl anion is highly stabilized by the resonance shown as below. It is evident that more the number of phenyl group attached to a carbon carrying the negative charge, greater will be the dispersal of negative charge due to large number of contributing structure. That is why diphenyl methyl carbene is more stable than benzyl carbene. 3 more contributing structure. For the same reason, triphenyl methyl carbanion is more stable carbanion. 6 more contributing structures. The carbanion obtained by removal of alpha hydrogen from a carbonyl compound are also stabilized by resonance as shown below. Free radical. What are free radical? A free radical is an atom or a group of atom having an odd or unpaired electron. It is noted by putting a dot against the symbol of atom or a group of atom. For example, Cl free radical stand for a chlorine free radical, while CH3 denote a methyl free radical. Free radicals are electrically neutral species which are usually formed by homolytic cleavage of a molecule in reaction taking place in a gaseous phase or in non-polar solvent. For example, chlorine free radical, benzoyl peroxide converted into benzoyl oxide free radical. Due to the presence of odd electron, free radical are paramagnetic in nature. Free radical are highly short-lived species. They are extremely reactive, and as soon as they are formed, they immediately participate in some further reaction. Their great reactivity is due to tendency of odd electron in them to get paired up. Formation of a free radical. They are main method by which free radicals are usually formed. First, by thermal or a photochemical homolysis of a covalent bond. For example, tetramethyl lead. When we heat it, it converted into lead plus methyl free radical. Benzoyl peroxide converted it into benzoyl oxide free radical. When we heated phenyl free radical plus carbon dioxide. Diacetyl converted into, in the presence of sunlight, converted into acetyl free radical. By oxidation reduction reaction involving gain or loss of a single electron. For example, carboxylic ion in the presence of electron give carboxylic free radical converted into alkyl free radical plus carbon dioxide. Structure of a free radical. In may be pointed out that in case of free radical containing carbon, the state of hybridization of a carbon atom having odd electron is not clearly established. However, there is a strong evidence to indicate that most of alkyl free radicals such as methyl radical are actually planar. This means that the carbon atom carrying the odd electron is in sp2 hybridized state. The three coplanar hybrid orbitals are involving in the formation of a three single bond with other atom. The unhybridized p orbital, which lie in a single plane of a straight line to the plane of a hybridized orbital carrying the odd electron. The bond angle around the carbon carrying the odd electron is approximately 120 degree each. Classification of free radical and their order of stability. Alkyl free radical are classified as primary, secondary or tertiary according to the odd electron is carried by the primary, secondary and tertiary carbon atom. But methyl free radical having only one carbon is treated as a special case. Thus we have methyl free radical, ethyl free radical primary, isopropyl free radical secondary, tertiary butyl free radical tertiary. The order of stability of different types of free radical relative to the alkane from which they are derived as follows. Decreasing in order, tertiary, secondary, primary, methyl. This order is derived from the bond dissociation energy involving in the formation. The lesser the bond dissociation energy in the formation of free radical, the more the stability. To illustrate the above statement, let us consider homolytic fusion of an alkane into an alkyl radical and a hydrogen atom. That is, it is apparent that the hydration energy such as dissociation process must be equal to bond dissociation energy of the bond between the concerned hydrogen and carbon of an alkyl group. A study of hydration energy of several reactions involving the dissociation of a different alkane to form different classes of alkyl radicals showed that the amount of energy required to form various classes. A study of hydration energy of several reactions involving the dissociation of a different alkyl to form different classes of alkyl radicals showed that the amount of energy required to form various classes of alkyl radicals are in order. Decreasing order in methyl, primary, secondary, tertiary. If more energy is required to form one radical than the other, it means the relative to the alkane form when it is formed. The radical contains more energy than the other and is hence less stable. Thus, it may be concluded that relative to the parent alkane in each case of the order of stability of free radical is tertiary, secondary, primary, methyl. It may be emphasized that this order is based only on the basis of in the energy between the alkyl radical and the parent alkane in each case. As such, it does not reflect the order of absolute stability of individual radical. To make this point clear, let us consider the case of methyl radical and ethyl radical, which is simplest primary radical. The difference in energy between the methane and methyl radical. Hydration energy from the reaction methane and methyl radical being 433 kJ is more than the difference between ethane and ethyl radical. hydration energy for the reaction ethane and ethane radical being 410 kilojoule. This merely means that stability of methyl radical related to methane is lesser than the stability of ethyl radical related to ethane. Explanation of relative stability of alkyl free radical. First, hyperconjugation. The relative stability of alkyl free radical are explained primarily in terms of a concept of hyperconjugation. With the conception of a methyl free radical or other free radical undergoes hyperconjugation through overlap between a sigma orbital of alkyl group and p orbital containing the order odd electron, taking to represent an alkyl free radical in general delocalization through sigma p orbital overlap may be shown as in adjacent figure. As a result of overlapping, the delocalization electron help in binding together three atoms, two carbon and one hydrogen to some extent. In terms of a resonance, the above situation may be represented by saying that the given alkyl free radical is a resonance hybrid of a two contributing structure as shown below. This means that the carbon-hydrogen bond is slightly less than a single bond, while carbon-carbon bond has some double bond character and the odd electron is partially present on a hydrogen atom. The actual number of a contributing structure of the extent of a delocalization of odd electron depend upon the nature of alkyl radical. The more the number of a contributing structure of the more extensive the localization, the more stable is the free radical. Let us compare the relative stability of methyl and ethyl radical. In methyl radical, hyperconjugation is not possible and no delocalization of odd electron take place. But in ethyl radical, 1 degree, there is a considerable delocalization of odd electron due to contributing from normal structure and 3 hyperconjugation structure as below. As a result, stabilization due to resonance or delocalization electron radical is about 225 kJ per mole more than the methyl radical. As we pass on the isopropyl radical, it will have 6 hyperconjugating contributing structure in addition to normal structure as given below. Due to greater delocalization result from more contributing structure, isopropyl free radical is more stable than methyl free radical to extent of 37.6 kJ per mole. Similarly, tertiary butyl radical 3 degree is stabilized to extent of 50 degree kilojoule per mole since it has 9 hyperconjugation structure in addition to a usual structure and therefore very extensive delocalization of electron take place. In general, the order of stability of alkyl radical is tertiary, secondary, primary and methyl. Free radical. Second, resonance or conjugation. Like carbocation and carboanion, free radical exhibiting resonance or a conjugation are also more stable than simple alkyl radical. For example, allyl free radical is more stable than alkyl free radical, while the former is stabilized by resonance. Similarly, benzene free radical is slightly stable by resonance as being shown. It can be readily understood that triphenyl methyl free radical is very highly stabilized by the resonance due to the presence of a 3-phenyl group attached to a carbon carrying the odd electron. Determination of a stability of some common free radical of a different kind. The relative stability of free radical can be assumed by determining homolytic bond dissociation energy of RH bond, carbon and hydrogen bond. The relative stability of some common free radical are given below in a decreasing order. Carbene. What are carbene? Carbene are a neutral divalent chemical species in which a carbon is covalently bonded to two atoms and have got two non-bonding orbitals having two electrons between them. In other words, carbene considered a neutral carbon atom having 6 electrons in the valence shell, out of which 2 are unshared. The most common carbene are CH2, methylene and CCl2, dichloromethylene. Carbene are highly reactive species having a very short life. Type of carbene. An interest feature of a carbene structure is that it may exist in two distinct states. First, singleton carbene. These are carbene in which unshared electrons are paired such that they are present in different orbitals. Second, Triplet carbene. These are carbene in which unshared electrons are not paired, such that they are present in different orbitals. For example, methylene carbene can have either of the following two structures depending upon the mode of a formation. Singleton methylene, unshared electron paired, or triplet methylene, unshared electron not paired. Triplet carbene represent biradical, divalent free radical. Formation of a carbene. There are two methods generally employed for the generation of carbene. First, by the thermal or photochemical decomposition of aliphatic diazo compound ketose or a cyclopropane or oxirane. For example, diazomethane in the presence of heat or sunlight converted into methylene carbene. Ketane in the presence of sunlight or heat converted into methylene carbene. Phenyl cyclopropane in the presence of sunlight or heat converted into methylene carbene. Second, by the action of a base on a suitable halogen compound. This method is usually employed for the generation of a halogen carbene, and the base commonly used is potassium tertiary bioxide. For example, chloroform plus tetrabioxide ion converted into chloroform ion. Chloroform carbene. It may be noted that in the above reaction, H positive and Cl negative are removed from the same carbon such that alpha elimination take place. A well-known example of a reaction in which carbene is formed as an intermediate is Riemer-Tiemer reaction of a phenyl to give salicylic aldehyde. It involves the formation of a dichlorocarbene as an intermediate. Phenol plus CHCl3 plus potassium hydroxide converted into salicylic acid plus KCl plus water. Structure of a carbene. In singleton carbene, the central atom is in a state of sp2 hybridization of the 3 sp2 hybridized orbital. Two are used in forming two single bonds with the monovalent atom or a group attached to a carbon. The third sp2 orbital containing the unshared pair of electrons, while the unhybridized p orbital is empty. In triplet carbene, the central atom is in the state of sp hybridized. The two sp hybridized orbitals are also used in forming single bond with the two monovalent atom or a group attached to a carbene. The two unhybridized orbitals contain one unshared electron each. Relative stability of carbene and its explanation. It has been found that triplet carbene are lower in energy and therefore more stable than a single carbene. This is because placement of two electrons in a single orbital in a singleton methyl involves electron repulsion energy, which must be overcome to pair the two electrons in a same orbital. On the other hand, in a triplet carbene, the two electrons occupy different orbitals and the electron repulsion is much less. As a result, singleton methylene have higher energy than triplet methylene. The difference in energy is about 37.6 to 46 kJ per mole. Comparison of a singleton and triplet carbene. Singleton carbene. In this, two unshared electrons are present as a paired in one orbital. Triplet carbene. In this, the two unshared electrons are present as two unpaired electrons in different orbitals, and thus it represents a biradical. This is singleton carbene. This is a relative less unstable. Triplet carbene. This is a relative more stable. Singleton carbene. The central atom is sp2 hybridized. Triplet carbene. The central atom is sp hybridized. Nature of a reagent. When two substances react together, one of the substances is regarded as an attacking reagent while the other is as the substrate. The substance which get attacked. The new substance formed as a result of a reaction is called product. The occurrence of a chemical reaction may be depicted as substrate plus attacking reagent converted into product. It may be pointed out the term attacking reagent is usually employed for the substance whose presence brings about a chemical change in the given substance, such as substrate, to form the product. But the use of two terms is purely related. A particular substance may be termed as substrate in one reaction and an attacking reagent in other. However, the following conversion of a generally following in the use of a two term. First, in the reaction between an organic and inorganic substance, the organic substance is treated as the substrate while the inorganic substance is taken as attacking reagent. For example, iodoethane substrate plus aqueous potassium hydroxide attacking reagent converted into ethanol plus potassium iodide. Second, in a reaction between two organic substances, the substance which implies the carbon atom in the formation of a new bond between carbon atom and heteroatom is treated as substrate. The other substance is taken as attacking reagent. Ethanoic acid substrate plus attacking reagent give ester new bond formation. Third, in a reaction between two organic substances involving the formation of carbon-carbon bond, one of the substances is arbitrarily assumed to be substrate while the other is taken as attacking reagent. Benzene substrate, ethanol chloride attacking group. Give this plus HCl. Classification of a reagent. There are three types of attacking reagent taking part in organic reaction. These are: first, free radical. Their formation and reacting has already been discussed. Second, electrophilic reagent. An electrophilic reagent or an electrophile, such that electron-loving particle, is a reagent containing an atom which is deficient in electron. Because of the presence of electron-deficient atom, such as reagent tried to seek electron from other sources and thus behave as a Lewis acid. It attacked a molecule at a point of high electron density. Type of electrophilic. There are two types of electrophilic: positive charge ion or positive electrophiles. Positive charge ion such as hydronium ion H positive, hydronium ion H3O positive, hydrogen ion H positive, chloronium ion Cl positive, nitronium ion NO2 positive, and carbocation act as electrophilic reagent. Second, neutral electrophilic. They are electrophilic reagent in which electron deficient atom does not carry any charge. For example, AlCl3, FeCl3 and BF4 being two categorized. These are the certain substances in which the central atom has a complete octet of electron and still it has a tendency to coordinate more electron due to presence of empty d orbital. SnCl4 afford an example of such as electrophile. Carbene also act as electrophile because the carbon is them has only 6 electrons rather than an octet. Reaction involving electrophile reagent are also known as electrophilic reaction. Third, neutrophilic reagent. A neutrophilic reagent or nucleophile, such that nucleus-loving particle, is a reagent containing an atom having an unshared or a lone pair of a valence electron. Because of free pair of electrons, such as reagent is in search of a site with which to share electron and in this way behave as a base. Lewis concept of a base. It attacks a molecule at a point of a low electron density. For example, considered a OH negative hydronium ion. The oxygen present in ion contain unshared pair of electron. Due to the reason of OH negative ion attacked an molecule containing a center of a low electron density, so that to share the electron at the point. Type of nucleophilic. Nucleophilic are also two types: negative nucleophiles and negative charge ion. All negative charge ions such as hydroxyl ion OH negative, halide ion X negative, alkoxide ion RO negative, cyanide ion Cn negative, and carb anion act as nucleophilic reagent. Second, neutral nucleophiles. These are nucleophile reagents which contain atom with lone pair of electron but do not carry any charge. water H2O, ammonia NH3, and alcohol ROH are neutral nucleophiles. Reacting involving nucleophilic reagent are also known as nucleophilic reaction. To be precise, all electrophiles and nucleophiles should be capable of forming covalent bonds when they participate in reaction. For this reason, positive ions such as sodium ion having noble gas configuration are not treated as electrophile because they cannot be formed covalent bond as they already have noble gas configuration. Classification of organic reaction. The organic reaction may be broadly classified into following categories. These are substituent or displacement reaction. Second, addition reaction. Third, elimination reaction. Fourth, rearrangement reaction. Fifth, isomerization reaction. Sixth, condensation reaction. Seventh, molecular reaction. First, substituent reaction. A substituent reaction is that which involves the direct replacement of hydrogen atom or some other group of a molecule by some other atom or a group without any changing in the structure of a remaining part of a molecule. The product obtained is called substituent product, and the new atom or a group which enters the molecule is called substituent. For example, when chlorine reacts with methane in the presence of diffusion sunlight, the hydrogen atom are replaced by chlorine atom, one after the other, leading to the formation of substituent product. Methane plus chlorine converted into methyl chlorine plus HCl. Similarly, the reaction of a methyl iodide with an aqueous solution of potassium hydroxide to form methyl alcohol in a substituent reaction. Methyl iodide plus potassium hydroxide converted into methyl alcohol plus potassium iodide. Substituent reaction may involve free radical, electrophilic, nucleophilic reagent. According, they are subdivided as free radical substituent reaction first. For example, halogenation of an alkane is a free radical substitution reaction. Chlorine Cl2 in the presence of sunlight converted into free radical by homolytic cleavage. Methane plus free radical chlorine converted into free radical methane plus HCl. Free radical methane plus Cl chlorine converted into chloromethane and free radical chlorine, and so on. Second, electrophilic substitution reaction. Nitration and sulfonation of a benzene are important examples of electrophilic substitution reaction. Benzene plus nitronium ion converted into nitrobenzene plus H removed by a base. Third, nucleophilic substituent reaction. Substituent reaction of alkyl halide are nucleophilic substituent reaction. Methane iodide plus oxyl hydryl oxide converted into methanol plus iodine. Addition reaction. An addition reaction involves the combination between the molecule of two reacting substances to form a single compound known as addition product. One of the reactant in such reaction always contains double or triple bond in its molecule. For example, ethylene plus bromine converted into ethylene dibromine. Addition reaction may also involve free radical, electrophilic or nucleophilic reagent. As such, they are subdivided as free radical addition reaction. Addition of HBr to alkene in the presence of benzyl peroxide is a well-known example of free radical. Propene plus HBr converted in the presence of benzoyl peroxide converted into N-propyl bromide. Second, electrophilic addition reaction. Most of addition reaction of alkene are electrophilic reaction. Third, nucleophilic addition reaction. Aldehyde and ketone undergoes nucleophilic addition reaction. Aldehyde plus Cn negative converted into acetaldehyde cyanohydrine. Elimination reaction. These reactions involve the loss of an atom or a group of atoms from a molecule to form compound containing double or triple bond. Thus, these reactions are initial. The reverse of addition reaction. The common reaction of this type involves the elimination of atom or a group from adjacent carbon atom to yield alkene. For example, propyl chloride plus alcoholic KOH converted into propylene. Elimination reactions are further divided into two types as given below. First, unimolecular elimination (E1 reaction). These are elimination reactions in which rate determining step involve only one molecule. For example, dehydrohalogenation of a tertiary alkyl halide usually proceeds by E1 mechanism. Tertiary butyl chloride plus alcoholic KOH converted into double bond 2-methyl propene plus KCl plus H2O. Second, bimolecular elimination reaction. These are elimination reactions in which rate determining step involve two molecules. For example, primary alkyl halides such as N-propyl chloride shown above generally undergoes dehydrohalogenation by E to M mechanism depending upon the relative position of atom or group eliminated. These reactions are also depend upon as alpha, beta, gamma elimination reaction. Second, alpha elimination reaction. These are the reactions in which loss of two atom or a group occur for a same atom of substance. Chloroform plus hydroxy ion converted into dichlorocarbene plus water plus chlorine ion. Beta elimination reaction. In this reaction, loss of two atom or a group occur from adjacent atom of a substance. For example, ethanol in the presence of concentrated H2SO4 converted into ethane. Gamma elimination reaction. In this reaction, loss of two atom or a group occur from alpha and gamma position of a molecule, giving rise to the formation of a third member chain. 1,3-diborane propane in the presence of zinc dust converted into cyclopropane. This reaction is also known as Freund reaction. Third, rearrangement reaction. This reaction involves either the migration of a functional group from one atom to the other or the complete rearrangement of a chain of a carbon atom present in a compound to form a new product. For example, 1-bromobutane in the presence of AlCl3 and 575 degree Kelvin converted into 2-bromobutane. Next example, N-butane in the presence of AlCl3 and HCl converted into 2-methyl propane. These rearrangements also take place through the formation of electrophile, nucleophile and free radical intermediate. It is interesting to note the preparation of a first organic compound such as urea of synthetic in a laboratory involve a rearrangement reaction. Ammonium cyanide heated converted into urea. Fourth, isomeric reaction. This reaction involves the conversion of one isomer into another so that the molecular formula and carbon skeleton of a reactant and product always remain the same. For example, conversion of a transmission to butene to cis-2-butane and vice versa is a geometric isomerism. For example, trans-2-butane in the presence of sunlight converted into cis-2-butene. Fifth, condensation reaction. These are reactions in which two or more molecules of a same or different reactant combine to form product with or without the elimination of a simple molecule such as water or alcohol. For example, when acetaldehyde treated with dilute alkaline, two molecules of acetaldehyde combine with form 3-hydroxybutanol. This reaction is called aldol condensation. Aldehyde plus CH3COHO in the presence of dilute NOH converted into 3-hydroxybutanol or aldol. Molecular reaction. These are reactions which involve reorganization of a covalent bond either intramolecular or intermolecular through cyclic transition state under the influence of heat or light. These reactions do not require any catalyst or no ionic or free radical intermediate is involved. They are collectively called pre-cyclic reaction. Electrocyclic or cycloaddition reaction are typical example of such reaction. First, electrocyclic reaction. This reaction involves conversion of an acyclic diene to a cyclic alkene and vice versa. For example, buta-1,3-diene in the presence of sunlight converted into cyclotransition state, cyclobutene. Second, cycloaddition reaction. These reactions involve addition of two unsaturated molecules of the same or different substance to form cyclic product. An example of this type 4 plus 2 cycloaddition reaction give below. The student will come across the detailed mechanism of various reactions at appropriate place in the text. Energy change during reaction. All chemical reaction involving the break and making of a bond, since energy is required to breaking a bond while energy is released in a formation of a bond, the occurrence of a chemical reaction is always accompanied by energy change in one form or the another. We will therefore now present briefly certain basic concepts regarding energy change such as enthalpy of reaction, enthalpy of activation and transition state. Heat or enthalpy of reaction. Heat or enthalpy of reaction is the total energy change with accompanied the conversion of a definite number of molecules as required by the balance equation of reactant into product. It is possible to calculate the enthalpy of a reaction on the basis of a bond dissociation energy of various bonds broken and formed during the reaction. For enhance, let us consider the following hypothetical reaction. AB x1 plus CD x2 converted into AC x3 plus BD x4. Let us suppose that x1, x2, x3 and x4 represent the bond dissociation energy of the respective bond involved in a reaction. During the reaction, two bonds AB and CD are broken while two new bonds AC and BD are formed. The two bonds broken require a total of x1 plus x2 kJ per mole of energy, while the two bonds formed liberate to total energy of x3 and x4 kJ per mole of energy. Therefore, the total energy change during the reaction, or in other words, heat of a reaction, should be x1 plus x2 minus x3 plus x4. It is apparent that if the energy consumed such that x1 plus x2 is more than energy released such that x3 plus x4, therefore would be overall consumption of energy such that the reaction would be endothermic and enthalpy of reaction would be have a positive value. On the other hand, if energy consumed x1 plus x2 is less then the energy release x3 plus x4, therefore would be net liberation of energy such that the reaction would exothermic and the heat of a reaction would be have negative value. Thus the reaction between methane and chlorine. On the other hand, the reaction between methane and iodine is an endothermic reaction. Methane plus iodine give iodomethane plus HI. Enthalpy of reaction 433 plus 151 minus 234 plus 297 give 53 kilojoule. Energy of activation theory, collision theory. An important feature of most of the reaction, whether endothermic or exothermic, is that the reaction requires some extra energy for the reaction to take place. To understand the reason for this, let us recall that according to collision theory of reaction, the primary condition for a reaction to take place is that the reacting particle must come in contact or collide with each other, but all such collisions do not result in the formation of product. In order to effective in bring about the reaction, a collision should fulfill two conditions. First, the colliding particle must have certain minimum amount of energy known as threshold energy. The colliding particle must be properly oriented with respect to each other at the time of a collision. As far as the energy factor is considered, most of the reactant molecules do not possess sufficient energy in their ground state and effective collision to take place. As a result, when such molecules collide with each other, no bond breaking and making take place, and the collision particle bounce back as such. Therefore, extra energy is needed by the reactant to form the product. The minimum amount of additional energy required by the reactant to undergo effective collision is known as activation energy. It is numerically equal to the difference between threshold energy and the ground state energy of the reactant. That is, Activation energy is equal to threshold energy minus ground state energy. Most of the organic reactions have activation energy in the range of 40 kJ to 150 kJ per mole. If the activation energy has a low value, the reaction can take place even at room temperature. On the other hand, the reaction with high activation energy takes place only on heat. Energy barrier to the reaction. The concept of activation energy means that the reactant have be activated or rise to a higher energy level before they form the product. In other words, there exists a certain energy barrier between the reactant and the product, in depicting the progress of a reacting. The barrier is generally represented as the energy hump, which has to be surmounted before the reaction can be completed. It may be compared to a path on the top of a hill separating two hills on the two sides of hill. To move from one valley to the other, one must move with the hill and cross the pass. Similarly, the reactant must move with the energy level and cross the energy barrier or hump to yield the product. It is interested to note that even through a chemical reaction involving breaking and making of a bond, the two processes are not perfectly synchronized. At the same time, the energy released through bond formation is not completely available for a bond fusion. This also explains why the reactant requires extra energy for the reaction to take place. Gift free energy change. Gift free energy change del G is a very useful parameter for determining the feasibility and direction of occurrence of a reaction. It is related to change of enthalpy and change in entropy as follows. Gibbs free energy is equal to change in enthalpy minus change in entropy. When all the substances are in their standard state, the relationship may be written as del G naught is equal to del H naught minus T del S naught. The enthalpy term del H naught is directly related to the bond strength in the starting with substance and the product. The entropy term del S naught is a measure of a change in the amount of a molecule randomness or disorder caused by reaction. A reaction takes place in the forward direction only if it has a negative value of del G, such that free energy of a product is less than that of reactant. On the other hand, a positive value of del G means that the reaction has tendency to take place in a backward direction. In case of equilibrium reaction, the equilibrium constant K is related to del G naught and del G naught is equal to minus 2.303 RT log K. Transition state theory energy diagram of a reaction. The transition state theory has been very useful in understanding the mechanism of organic reaction and the energy change take place during the reaction. According to this theory, the reaction do not change directly to the product. But what happens is that when the reactant molecule come in a contact with each other, it lead to the formation of highly unstable arrangement of atoms whose energy corresponding to the energy barrier separating the reactant and the product. The high energy species that form is known as activated state and transition state. For example, in a single step reaction represented by an equation A plus B minus C converted into A minus B plus C, the high energy transition state may be represented as the dotted line indicates partially bond. The transition state mainly represents a probability arrangement of atom corresponding to the energy barrier in which a bond is partially but not completely broken and a new bond has begun to form but not yet completely formed. It does not represent a substance which can be isolated or even detected. As soon as this transition state is formed, it split into the product, thus the complete reaction sequence may be represented as the free energy difference between the reactant and transition state is known as free energy of activation denoted by del G. It determines the rate at which reactant reach the transition state which in turn determines the rate of a reaction. A small amount of del G means that there is only small difference in energy between the reactant and transition state and therefore the reaction will place rapidly. Conversely, a large value of del G means that the reaction would take place slowly. The transition state is in equilibrium which reactant and its concentration is determined by equilibrium constant K which is related to the free energy of activation. Del G star is equal to del H star minus T del S star is equal to minus 2.303 RT log K star, where del H star is the enthalpy of activation and del S star is the enthalpy of activation. Note the superscript star known as double Bragg, is always used non-suffering to activate parameter involving the transition state. Figure 2.3 show the free energy of reactant transition state and product free energy of activation del G double drag involving in the formation of transition state and the net free energy G change del G naught for a single step reaction. Such a diagram which show the energy of a variation species and the energy change taking place during the process of reaction from beginning to end is known as energy profile or energy diagram of reaction. It is to be noted that the reaction enter diagram of all reactions are not similar to figure 3.2. On the other hand, each reaction has its own specific energy diagram depending upon the value of del G star and del G naught. Energy diagram for multi-reaction. A reaction can proceed from either to product either directly in a single step known as concerted reaction or it and take place through two or more steps which involve the formation of one or more intermediate. Since the reaction is directly converted into the product without the formation of intermediate substance in concerted reaction, the energy diagram of a such reaction has only two energy minima corresponding to the reactant and the product and an energy maximum corresponding to the transition stage as shown in figure 3.2. Most of organic reaction compound are multi-step reaction involving the formation of one or more reactive intermediate. Therefore, let us consider the complete energy diagram of a multi-step reaction with the help of a two-step reaction involving one reaction intermediate. Such a reaction involves the formation of a two transition state as shown below. Reactant transition state first, intermediate reactive intermediate transition state second, product. In such reaction, we draw the energy diagram for each of the individual steps and then join them in a middle as the product of a step 1 reactive intermediate act as the starting material of a step 2. Since the intermediate has higher energy than either the reactant or product, it is very reactive and may or may not be isolated. However, unlike the transition state, depending upon the transition state, the intermediate has measured lifetime. Depending upon the free energy of activation energy of a two transition state, the free energy diagram can be type 2 as shown below. First, if the free energy of activation energy transition state is more than that of a transition state. Second, the energy diagram as shown in figure 3.3. In such cases, the intermediate reaction gets converted into the product and can be seldom isolated. The step first of a reaction is the rate determining step of overall reaction. Figure 3.3 energy profile for a two-step reaction involving the first step is rating determining. Second, if the free energy of activation of a transition state is more than the transition state first, the energy diagram is as shown in figure 3.4. In case of the intermediate is rather stable and cannot be isolated. Figure 3.4 energy profile for a two-step reaction in which the second step is the rate determining step. The second step of each reaction constitutes the rate determining step of overall reaction. It may be noted out that for the many reactions which we study, the enthalpy change which take place during the reaction are much larger and much important than entropy change. Therefore, it is something found convenient to ignore the entropy change in such reaction. As a result, the reaction energy diagram may be drawn in terms of energy of activation energy EA in place of free energy of activation del G star. Similarly, the energy change take place during the reaction may be depicted in terms of a del H naught enthalpy of reaction instead of a Gibbs free energy at standard. It must be remembered, however, that activation energy is very closer to the free energy of activation, and enthalpy of reaction is very nearly to the Gibbs free energy. Figure 3.5 shown the energy diagram of an exothermic reaction in terms of activation energy, while figure 3.6 show the energy diagram of endothermic reaction. It may be noted from this diagram that first, the difference in energy level between the reactant and the transition state represents the activation energy. The difference in energy level between the reactant and the product represents the del H uh, enthalpy of a reaction or heat of a reaction. For an endothermic reaction, activation energy must be least as large as enthalpy of reaction, although generally it is large. For exothermic reaction, activation energy may be higher or lower. Generally, it is one of a lower side. Development and structure of transition state, Hampton postulates. In order to full understand reaction, it is necessary to complete understand the structure and energy of a transition state which lead to the formation of a product. But the transition state has only a transitory existence. As soon as it is possible during the course of a reaction, it changes into a more stable species. But it is possible to have an idea of a structure of a particular transition state from the reaction energy diagram with the help of a Hammond postulate. Hammond 1955 advanced a generalization known as Hammond's postulate to correlate the energy and the structure of a transition state. According to this postulate, structure of a transition state most closely resembles the structure of a stable species that lie closest to it in energy. For example, in a strongly endothermic reaction, the energy level of a transition state is much closer to that of a product than reactant. Therefore, the transition state would be expected to closer resemble the product in structure as well. On the other hand, in a strongly exothermic reaction, the transition state is energetically much closer to the existence than the product. As a result, it has the stronger resemblance to the reactant structurally. For a two-step reaction, the first transition state may be structural, resemble either the original reactant or the intermediate, whichever is closer to its in energy. The second transition state in turn may resemble structural, either the intermediate or the full product according as which is energetic close to it. Effect of a catalyst on the transition state. Many reactions which we shall study involving the use of some suitable catalyst to increase the rate of a reaction. What the catalyst does in such reaction is to provide an alternate path from a reactant to produce with a lower energy transition state. Thus the catalyst lower the energy of activation required for the reaction so that the rate of a reaction increase. It must be pointed out, however, that the del H enthalpy of a reaction or del G gives free energy for the reaction remain unchanged even in the presence of a catalyst. Assigning formal charge or intermediate and other ionic species. While studying the various reaction intermediate, it has been found that these species may either carry positive or negative charge, or they may be neutral in a character. In order to predict whether a given species carry some charge or not, we now present a very simple method known as the formal charge method for exchange explanation or intermediate. Formal charge. It is the amount of positive or negative charge which can be assigned to certain atom of a species in order to know whether the species as a whole carried some charge or not. The calculation of a formal charge involving the comparison of a number of valence electron in a neutral atom in the free state and the number of valence electron associated with the atom in the bond state. The difference between the two values given the formal charge on an atom in a given species, that is, formal charge on an atom in a given species, number of valence electron in the free atom, minus number of valence electron in a bonded atom. Calculate the number of valence electron in the bonded state. To calculate the number of valence electron associated with an atom in the bonded state, first, the number of electrons shared between two atoms or are dividedly equal between the two atoms that share them. This means that even though the electrons are shared between two atoms, it is still true as if each atom owns one electron of the shared pair. The number of non-bonding valence electrons of an atom are assigned executively to that atom. The sum of a number of electrons assigned as above given the number of valence electrons in the bonded atom. This is also sometimes referred to as the average electron, that is, number of electrons in a bonded atom or average electron is equal to 1 by 2 into number of shared electron plus number of non-shared bonding electron. Therefore, the formal charge on a bonded atom may also be represented as formal charge on an atom is equal to number of valence electron in the free atom minus 1 by 2 into number of shared electron plus number of non-bonded electron. Formal charge on a species as a whole. Knowing the formal charge on each atom in a given species, the formal charge on the species as a whole can be found by adding together the formal charge on various atoms. That is, formal charge on a species is equal to total of a formal charge on all the atom in the given species. We now elucidate the complete produced by considering the example of the simplest molecule, methane. It is apparent from the structure that carbon is surrounded by 8 electrons which are shared with 4 hydrogen atoms. Therefore, the number of valence electrons associated with carbon in methane is 1 by 2 into 8 is equal to 4. Since the number of electrons in a free carbon atom is also 4, the methane carbon is electrically neutral. In other words, there is no formal charge on carbon atom in methane. We can also arrive at the same conclusion directly. Formal charge on a carbon is equal to number of valence electron in a free carbon minus 1 by 2 number of shared electron plus number of non-bonded electron. 4 minus 1 by 2 into 8 plus 0. 4 minus 4, 0. Each hydrogen atom in methane is surrounded by 2 electrons which are shared with the carbon. Therefore, formal charge on each hydrogen is 1 minus 1 by 2 into 1 plus 0 to 0. Formal charge on a methane molecule. Formal charge on a carbon plus 4 into formal charge on hydrogen. 0 plus 4 into 0 is equal to 0. It is of course well known that methane molecules have no net electrically charge. Let us now compute the formal charge on some of intermediate already studied. First, free radical. It has been stated earlier that free radicals are experimentally neutral species. To justify this, let us consider the methyl radical CH3 dot, which is the simplest free radical. The carbon is surrounded by 6 bonding electrons shared with 3 hydrogen and 1 non-bonding electron. Each hydrogen is surrounded by only 2 shared electrons. Therefore, formal charge on a carbon 4 minus 1 by 2 cross 6 plus 1 is equal to 0. Formal charge on each hydrogen 1 minus 1 by 2 into 2 plus 0 is equal to 0. Formal charge on methyl radical is equal to formal charge on carbon plus formal charge on hydrogen. 0 plus 3 cross 0 is equal to 0. Second, carbon cation. The positive charge on a carbon cation may be verified by considering the case of a methyl carbocation. It may be easily seen that formal charge on carbon is equal to 4 minus 1 by 2 cross 6 plus 0 is equal to plus 1. Formal charge on each hydrogen 2 minus 1 by 2 cross 2 is equal to 0. Formal charge on a carbocation 1 plus 3 cross 0 to 1. Carbon anion. It is well known that carbon anion are negative charged species in which a carbon atom carries negative charge. To rationalize this, we can consider the structure methyl anion. Formal charge on it 4 minus 1 by 2 into 6 plus 2 is equal to minus 1. Formal charge on each hydrogen 1 minus 1 by 2 cross 2 plus 0 is equal to 0. Formal charge on carbanion minus 1 plus 3 cross 0 to minus 1. Carbene. The simplest carbene in methyl is methyl. Formal charge on carbon 4 minus 1 by 2 cross 4 plus 2 is equal to 0. Formal charge on each hydrogen 1 minus 1 by 2 cross 2 is equal to 0. Formal charge on a carbon 0 plus 2 cross 0 is equal to 0. Carbene are neutral species. Fifth, nitrates. The neutral character of nitrates may be verified that the formal charge of calculation on methyl nitrite in Formal charge on carbene 4 minus 1 by 2 into 8 plus 0 is equal to 0. Formal charge on nitrogen 5 minus 1 by 2 cross 2 plus 4 is equal to 0. Formal charge on each hydrogen 1 minus 1 by 2 cross 2 is equal to 0. Formal charge on nitrogen is equal to formal charge on carbon plus formal charge on nitrogen plus 3 into formal charge of hydrogen. 0 plus 3 plus 0. Chapter complete. Thank you.